here's a mini review where we can solve differential equations by separating the variables. Sometimes our variables are already separated and things are easy. We're given our differential equation. Here's a nice straightforward one. Dx dt is just equal to x. And we're given an initial condition that when x is 0, in this case t would be 3. Because it's, or sorry, dx dt when t is 0, x is 3. So what kind of equation might this be? This looks like a particle traveling along the x-axis based on time. So your position on your x-axis with respect to time, at time 0, it's at position 3. So how do we do this? How do we separate things? Well, first of all, we would like to put our x on the side with dx and our t on the side with the t's, which there are none. So if you imagine this, okay, I can multiply both sides by dt, but then my x is on my side with the dt. I'd have to divide both sides by x to get my x on the side with the dx and my t, which there are none. In other words, it's just a constant 1 on the side of dt. I can now integrate both sides after doing that. Integrating this side with respect to x will give me the natural log of the absolute value of x. Integrating this side with respect to t, well, integral of 1 is just t, and they would be both plus c. You can do that plus c on either side. It really doesn't matter. So we have a little bit of freedom with the plus c. There would be a plus c on both sides. Those are both constants. You can always combine constants together and get another constant. So we're able to put the plus c in the end, basically wherever we would like. Now we have an initial condition. Our initial condition says when time is 0, oh, and we can rearrange this too. When time is 0, x is 3. Couple of little notes in this rearranging that was done here. So I took my natural log, I changed it to exponential form. Okay? So the base is e, the exponent is t plus c, would equal the absolute value of x. From here to here, I'm able to just take away the absolute value of x. Why? Well, if I think about my graph of e to the x, it's always positive to begin with. Doesn't matter what number you put in as an exponent, e to the exponent of anything is going to be a positive number. So at this point, I know that the right-hand side is positive, therefore the left-hand side has to be positive. The absolute values aren't necessary. Okay. So going from here, adding exponents, same as multiplying, this part right here is just a number, so we can write it out as c in front. E to the 0 is 1, so c happens to be 3. Okay? Would it have been wrong to plug in things earlier? You would have natural log of 3 equals 0 plus c. Is it wrong to have plugged it in earlier? No. You're going to find out you're going to be able to solve the same thing. What? Oh, wait a minute. Oh, we get different c's because our c's changed. So here, I would get c is equal to the natural log of 3, and then my initial equation would have been natural log of absolute value of x equals t plus c, and now my c is the natural log of 3. Question?
Which way do you prefer us to do?
Well, it depends on, in the end, you want an equation, and in this notation, the t is like your x, and your x is like your y. Okay? How do we normally write equations? We normally write equations as y equals, right? As the function, in this case, we would want to write our equation as x of t equals. So it makes sense to get my x by itself first. So the left-hand side is better, because what do I have to do here? I've got my natural log of 3, I've solved for c, but I would still need to rearrange now to get x by itself, which isn't necessarily hard. What would it be? My base is e, my exponent would be t plus the natural log of 3 is equal to x. This would be technically correct as well. If I wanted it to look exactly like this, notice you could write e to the t times e to the natural log of 3 equals x, and e to the natural log of 3 is just 3. They would both work out to be the same equation, whichever way you looked at it. So it's not like, oh, I chose the wrong path and didn't get there, okay? Both are going to be fine. Since they want an initial equation, either what's circled in the red box here, completely right. I don't need to simplify. So if I would have put a box here, this blue box, with the plus natural log of 3 in the exponent, perfectly fine, right? The AP course doesn't require you to do simplification in math, okay? Where do they test if you can simplify? In all their multiple choice questions, right? Because if you did the blue method and you got the answer in the blue box, but it didn't match your multiple choice, then you have to play around with your algebra to match it up. So there's often different methods to get to the same answer. This is a good example of one of those, but if it was long answer, you can leave it as either way. So here we have a dy dx. And our job, if we're going to separate the variables, is to get the dx on one side with the x's, the dy on the other side with the y's. You might like to do this extra step where you first multiply both sides by dx. Because in order to separate your variables, you need one side with dy, one side with dx. And then you have to use your algebra skills to say, how do I make sure the x's are on the sides with the dx, and the y is on the side with the dy. Here's my x. Does it make sense? I can't subtract it over. You might be tempted to be, I'd like to just subtract that x squared to the other side. But that x squared plus 1 is all being multiplied by the dy. So in order to get that x squared over to the other side, I have to move that whole factor to the other side. Opposite of multiplying would be dividing. So there's lots of places we can make small algebraic errors just in the setup. But once you get your x's on the side with the dx and your y's, or in this case it's just a 1 with the dy, the left side is really easy to integrate. It's just going to be y plus c. The right side, an x squared plus 1 on the bottom. That's our tan inverse function. And again, you could have written a C1 and a C2 on both sides. They're just going to get combined. Writing 1 plus C in the equation is fine. What's nice about this equation is it's already y equals. Like the last one we had to do some rearranging. This one's already y equals. So it makes sense to plug in right away. When x is 1, y is pi. Remember, what does tan inverse do? Tan inverse finds an angle. Is 1 on your pi plate? Is there any angle tan that gives you 1? Yes. Right? That's pi over 4. Could it have been 3 pi over 4 in quadrant 3? Tan of 3 pi over 4 is 1. Would you get this question wrong if you plugged in 3 pi over 4? Yes. Okay? So, it is true that tan of 3 pi over 4 is 1. But we have to remember that the tan inverse graph has a range from negative pi over 2 to pi over 2. This means you're only going to look negative angles in quadrant 4 and positive angles in quadrant 1. So a little reminder from our tan inverse unit that if you have a tan inverse question and it's a positive number, you're only looking in quadrant 1. If they had tan inverse of negative 1, you would look for a negative angle in quadrant 4. So then the only answer would be negative pi over 4. So we have to be careful. Well, I said 3 pi over 4 for 1. It should have been 5 pi over 4, quadrant 3. So pi over 4 is the only answer that allows us to solve for C. C is pi over 2. We put a box around our final answer. And we have found the particular solution. Oh, the next question was kind. They already separated the dy dx for you. Already have the y on the side with the dy, the x on the side with the dx. We can integrate right away. And both of those integrals are easy. Y squared over 2, x cubed over 3. Again, they would both have a plus c. If you wrote plus c on both sides. I guess the only danger of technically writing plus c on one side and plus c on the other is mathematically, if you have plus c on one side and plus c on the other and they're the same c, they should technically cancel out and be nothing. So then I guess you should write plus c1 and plus c2. But it's okay. So do you know what I'm saying? If I had done this, technically, if you're using a constant, that constant does represent a single number. We just don't know what that number is. We don't know what c is yet. If I write it this way, can you see that I could subtract c on both sides and they'd cancel out? So technically, if you're doing this, I guess it would make sense that one of them you write as c1 and one as c2. But it's okay to have already done that mental math and said, those will be combined, and then we'll get some new c, and I'll just put that c on the right-hand side. Could I get y by itself? Absolutely. I could get y by itself by square rooting both sides and adding a plus or minus. And then I could plug in 5. Still have that plus or minus. And then look what happens. Where's the c? The c is inside my square root. What do I have to do then? I have to square to get rid of my square root. Do you see that? Okay. So I think it's not bad if you know your initial conditions. Why not at this point, from here, you could have plugged in 5 for y. I'll do it in black. I could have plugged in already 5 for y and 3 for x. Oh, it's cubed. I did miss that. Is that not easier? Not having to worry about that square root? There's nowhere that it says you have to get y by itself before you plug things in. I know my x and my y values. Why not plug them in right away? Solve for my c. Then I would know that c was 7 inside of here. I could square root right at the end to get my final equation to be y equals at that point. Okay. So, the next page, I'd like you to try those 3 on your own. Oh, and yes, so on that last one we noticed was missing a 3 on the bottom there, so added that up. This next one, if you did your work and are checking, again, having the C out in front makes your life easier. Is it wrong if you would have done this? No. This is still, right? If you had moved your 1 over here, this is still a general solution. It still has y by itself, and it still has a c. In my mind, those are both equally the same. You could have had the plus c in the exponent. That would have been fine as well. But your plus c looked a little bit too low there. Technically, using your exponent laws, this would also be find, right? If you're adding exponents, that's the same as multiplying two powers with the same base, right? That's like unadding your exponent rule. So that would have been fine as well. Again, this probably doesn't show up as long answer on an AP exam. It shows up as multiple choice. So as multiple choice, if you had any of these three in red boxes or whatever shape I last drew, those are all right. But you have to be able to manipulate between them because the multiple choice doesn't look like it. That's the thing about multiple choice is like, I have the right answer. I know I have the right answer, but it doesn't match any of the answers they have. So then we have to go to our algebra and manipulate things around. So this exam is going to check, do you know your calculus? But do you know your calculus with exceptional algebra skills? We don't want you just knowing calculus. We also want you coming in with exceptional algebra skills as well. All right, and the one at the bottom. So here, as our setup, okay, I need to get my x's and my y's separated. First thing I'm going to do is I'm going to say, hey, e to the x minus y, I can use my exponent laws and write that as e to the x times e to the minus y. Then I can separate them and get my answer.